One of our I can statements involved ranking the nucleophilicity and or basicity of a set of organometallic species. And so to address this issue, what you really need to do is think about the stability of the anion that corresponds to the Grignard reagent that you're thinking about. From organic 1, you should remember that as the S character in a hybrid orbital increases, the orbital becomes more compact. You can see in the drawings here that the nucleus, which I'm indicating with a black dot, is positioned at the center of each of these orbitals. Remember, the nucleus is positively charged, and so the more fully it's surrounded by an electron cloud, the more stabilized that charge is going to be overall, and so the more stable your anion will be. If you look now at the sp, the bulk of the sp orbital is actually pretty close to the nucleus here, and then as we proceed toward the 2p orbital, the electron density gets farther and farther away. It's easiest to see that on the small lobe side of this orbital. So I'm just going to go ahead and highlight that for you in red. That overall, the distance between the nucleus and the outer edge of the molecular orbital is increasing as the S character decreases, with the largest distance being at the 2p position. And so if this cloud is containing the electrons, those electrons are going to be less stabilized by the nucleus the farther they are from the nucleus. So an anion in a 2s orbital is going to be significantly more stable than an anion in a 2p orbital. And the hybrid sp, sp2, and sp3 orbitals are going to lie along the continuum between 2s and 2p. So it's easy to get mixed up when you're thinking about hybrid orbitals because the larger number has less S character. So what you need to remember is that an sp3 orbital is a hybrid of an s and 3p orbital. So it's mostly made of p, right? So you can kind of think 1 out of 4 component orbitals is S in this picture, whereas here 1 out of 3 and here 1 out of 2. And of course in the 2s, it's only made of 1s orbital. Another way to view this concept is to look at the charge density profile of a series of molecules that have CH bonds that are hybridized differently. And so here on the left, you can see that ethane, as you know, is sp3 hybridized, and the color on the hydrogen there is just this kind of light teal. The closer we are in the spectrum to red, the more negative the charge, and the closer we are to purple, the more positive the charge. So you can see this hydrogen is not very positively charged. The hydrogen on ethene, which is sp2 hybridized, is significantly more positively charged than the sp3 ethane. And then ethyne, which is now sp, which is a significant amount of S character, has the most positive charge on the hydrogen. That means it has the lowest pKa value. It's the most acidic. So to take these concepts and join them together, overall we can think about reactivity and basicity of Grignards and organolithiums by considering the anion stability. So a sp anion is going to be much more stable than an sp2 anion, which is going to be much more stable than an sp3 anion. The corollary to that is that the most reactive Grignard reagent or organolithium, as shown here, is going to be the ethyl lithium, followed by vinyl lithium, followed by alkynyl lithium. The last way that we can think about this is to look at the electronegativity of these various species. And what we're talking about here is the electronegativity of the carbon of interest. So if we look at ethane, the electronegativity of this carbon is 2.3 compared to hydrogen at 2.1. So this is a true covalent bond, almost equal sharing of the pair of electrons. Now, ethene is going to be in between these two extremes, but overall, this carbon has more electron density from the covalent bond than the hydrogen does, and that's what makes this more positively charged and more easy to deprotonate. Ethyne is on the extreme end of this, so the electronegativity of this carbon is 3.3, and the hydrogen again is 2.1, and so you have a significant dipole moment toward the carbon. Positive charge on the hydrogen is much larger than in either of the two prior cases. So next we're going to look at the reactivity of these reagents with epoxides. And so I've chosen here to include two different types of epoxides, a terminal epoxide, meaning that we have a CH2 group on one side, and an internal epoxide, meaning that both of the carbons in the epoxide are substituted. So the first thing we need to remember is that Grignards and organolithium reagents are very strong nucleophiles. They really are not happy as this sort of anionic species. So what this means is that they're going to react similarly to how sodium hydroxide or other very strong nucleophiles you talked about in Organic 1 reacted with epoxides, which is to form the kinetic product. So what defines something as the kinetic product is that it's the product that comes from the pathway with the lowest barrier to reactivity. And so if you think about your choices, we have this carbon here that has a carbon substituent, and we have this carbon that has a deuterium and a hydrogen. Remember, deuterium is just a hydrogen with an extra neutron. So the question to ask yourself is, which of these sides is easier to attack with a nucleophile? And so the answer just comes down to sterics. The easier side to attack, and therefore the lower barrier, is going to be this side here with essentially two hydrogen atoms. So we'll go ahead and draw our reaction now. So this carbon is going to again act like R minus or methyl minus, and it's going to attack this carbon in an SN2 reaction. So that's nice. You get to start out here with a little bit of review. Remember that we have backside attack on this carbon, and that now our leaving group is going to be O minus, and we'll have inversion at this stereocenter. And so since the alkoxide that we're generating here can't be isolated as it is, like we can't just store this thing as this salt, it's not stable. The best practice is to quench the reaction. So quench is a term that means to get rid of all charged species on the molecule and any unreacted starting materials. And so the way we're going to do that is using a source of H3O+. And so a simple deprotonation event gives us the product alcohol. Now you want to take note of what we made here. We have synthesized a secondary alcohol. Throughout the course, you're going to want to take note of how you can view the products of the reactions we do, so that if you're encountering a synthesis problem, you'll see the secondary alcohol and think, oh, I can make a secondary alcohol from opening an epoxide that is a terminal epoxide. Or I can make a secondary alcohol from the reduction of a carbonyl. So you want to kind of categorize your reactions in this way, and don't forget the ones that you already learned in Orgo 1. So now let's move forward and try the second example. I'd encourage you to pause the video at this point and try this example on your own. Thanks for trying that on your own. And so now let's work through it together. Again, we have an epoxide, but now this one is an internal epoxide, meaning it's not on the last two carbons, but it's on two carbons that are contained within the rest of this substrate here. And so we need to check which side of this epoxide is going to be the least hindered. So over here, we have a methyl group and an ethyl group. So this carbon has 1, 2, 3 carbons attached to it. This carbon has 1, 2 carbons attached to it and a hydrogen. So this one is going to be less substituted than this one. So we want to attack this carbon, the less substituted side. You'll see how I kind of snaked my arrow around. That's because I want to draw on my paper that I'm attacking from the back side of the carbon leaving group bond. So it's a little weird when you're opening a ring because you need to essentially attack from the back of this bond that's in the ring. So that's what I'm trying to depict here. And if you want the correct answer, then this is also how you need to draw your arrows. Okay, so now check your paper and make sure that this is the product that you got from the first step. It's always a good idea to check how many carbons. So here we have 1 and here's 2, 1 and 2. Here there was 1 methyl group. We need to make sure we invert this stereocenter, which I did. I pushed these 2 groups up and I made the new bond come in the plane because it's displacing the group in the plane of the board. And we have N-propyl magnesium bromide as our nucleophile, so we have 1, 2, 3 carbons. And N, remember, means that the magnesium bromide is attached to the terminal carbon atom. Once again, we're going to quench this reaction using our H3O plus source. And so once again, we're going to take note of what we made, and that is a tertiary alcohol. So you can see that at this position, we have 3 carbon-containing substituents. That makes this a tertiary alcohol. So now we know that we can make tertiary alcohols from trisubstituted epoxides or oxiranes. Okay, so with that in mind, we can now move forward and see how we can apply these new reactions in synthetic design. So here we have 2 target molecules, and we're going to first start by just defining for ourselves what we're actually trying to make. Okay, so on the left we have a tertiary alcohol. That's the key functional group. Okay, and we have this kind of alkyl chain, which if we think about cutting this molecule into 2 parts, we might think about this group as a propyl group and this as a cyclopentane. So now if we look in the bottom right corner, we can see what kind of starting materials we're allowed to use in this problem. Okay, so I've called this the synthetic toolbox, and those are the starting materials and reagents that you're allowed to use, and you can use any solvents that you like. Okay, so we've identified that we have an N-propyl group, and so we might think about whether we could use N-propyl magnesium bromide, which is one of the available reagents. So to check whether that would be a reasonable reagent to use, what we're going to do is think about this backward. Okay, so instead of how can we add propyl magnesium bromide to something to get to this product, we can think, how can I break this molecule to generate a propyl anion, which is essentially what we're delivering when we use propyl magnesium bromide. Okay, so our first idea was to remove propyl anion. Okay, so we're going to do this by imaginary bond breaking. And when we do this kind of backward step, it's called a retrosynthetic step. And so we don't use this kind of arrow, we use this kind of arrow. That just distinguishes whether we're trying to build something or break something. So this is the bond breaking arrow. Okay, and if we break that bond, we're going to make propyl anion, which is what we're trying to do. And don't forget the other side, we now have a plus at this position. So now we need to think about what is going to react like this molecule. Okay, so one way to check on that is to look at the resonance forms of your cation. And when we do that, what we see is a protonated carbonyl. Now we don't have a protonated carbonyl or a non-protonated carbonyl in our toolbox. And in fact, this is a reaction we're going to learn in the next chapter. So we need to move on now to our second idea. The reason I brought up the first idea was simply to point out that you need to be adventurous when you're thinking about a synthesis and go ahead and write down whatever ideas you have. And if you get to something that you don't know what to do with, then you go back and try removing a different group from the molecule. So now let's think about how we might remove an ethyl anion, which would be what we can add by using ethyl magnesium bromide. So to do that, we're going to break this carbon-carbon bond because that's going to give us CH3CH2 minus, which we can get from ethyl magnesium bromide. And then we need to draw the other product of this arrow, which is the carbocation on this position. Now, primary carbocation is pretty terrible, but if we look what's nearby, we have the lone pair on this oxygen, and that's 1, 2, 3 atoms. So we can actually make that by opening an epoxide. So let's do it backward. Let's close the epoxide. Again, this is all a mental exercise. Okay, and now we aren't going to need this proton. Instead, we just need the epoxide. Now that's not in our synthetic toolbox, but we do have this precursor that has all the necessary carbons. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And we have MCPBA. And now you'll remember from first semester that you can make an epoxide from MCPBA and an olefin. So now that we've figured out what we need to use for our building blocks, we can write out the forward synthesis. So we start with the precursor that we found here with this exocyclic olefin. We're going to add MCPBA to get to our oxirane or epoxide. And then we're going to add our ethyl magnesium bromide. But remember, you need to include the workup step. And so you can just write H3O plus there. And that's going to give you your target molecule. Always, 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 when you're done with the synthesis, go back and count the atoms. So over here we have 1, 2, 3 carbons in our chain, and then we have the 5-membered ring and our alcohol. Here's our 5-membered ring, and then we just check 1, 2, 3. It looks silly in this simple of an example, but you'll see as the course goes on that it's actually really easy to lose a carbon, and then it's hard for us to give you all the points you deserve. So now that we've completed that example together, go ahead and try the second example on your own. The next reagent we're going to talk about is the Gilman reagent. And Gilman reagents are actually made from an organolithium and copper iodide. And these again have to be made in diethyl ether or THF, which is fine because that's how you will have made your starting organolithium in the first place. So take note that the stoichiometry in this reaction is 2 to 1, the organolithium to the copper iodide. Here I've written 0.5 equivs copper iodide, but you could just as easily write 1 equiv copper iodide and 2 equivs of the organolithium. So we'll draw out a simplistic mechanism here, keeping in mind that this is not likely how the reaction actually happens, but it's a way that you can keep track of where all the electrons are going and where the bond formations are coming from. So here we are going to have attack of our organolithium species on the copper iodide, and we'll kick out I-. This gives us an organocuprate intermediate and an I- as the counter ion. And then this is going to react again. Remember, we have 2 equivalents, or basically twice as many moles of organolithium as we have of copper iodide. And so our organolithium species is going to again come in and attack this copper here. There's no leaving group needed there. The products of this arrow are actually trickier than they might seem at first, so you need to keep track of what's happening with the electrons on your copper. So we started out with copper 1, and we added 2 electrons and we took away 2 electrons, so we still have copper 1 here. And then now here's the I- that balances this positive charge. We're going to add 2 electrons to this copper. So +1 and then -2 makes -1. So our formal charge on copper is now negative, and the counter ion for that is the Li+. So this thing overall is the Gilman reagent, or it's also called a dialkyl cuprate. And these Gilman reagents also react like a carbon minus, but it's important to distinguish these in a few ways from a Grignard reagent. First of all, take note that only one of the 2 alkyl groups on the cuprate is actually transferred to the product. The next thing to note is that a cuprate is actually significantly less reactive than an organolithium or a Grignard reagent. Finally, a Gilman reagent or organocuprate has different reactivity than organolithiums and organomagnesium halides. First of all, they can perform something called a Gilman coupling reaction, and second of all, they can participate in SN2 reactions on alkyl halides, which organogrignards and organolithium species cannot do. They can also open epoxides analogously to organolithium and Grignard reagents, and they do give the kinetic product, but since you have to make your cuprate from an alkyl lithium, there's really no point in taking your alkyl lithium, making an organocuprate, and then doing a reaction that you could have done with that organolithium reagent. So we're going to look next at the Gilman coupling reaction and then SN2 on alkyl halides. So in this example, we're going to start with butyllithium, and we're going to form the Gilman reagent by treating with half an equivalent of copper iodide in ether or THF, and that's going to give us the dibutyl cuprate. We're going to then treat that with a vinylic iodide here to get a new product as shown here. So essentially what we're doing is we're going to form a carbon-carbon bond between the carbon where our lithium was attached, and the carbon on this halide. So the way we do that, though, is we have to go through the cuprate. This carbon needs to be attached to copper in order to do the reaction that makes the carbon-carbon bond. Again, it's really important that you keep track of the atoms in your reaction. So here I've numbered the atoms in the butyl group. Those occur in the product here. And then I numbered our vinylic iodide, 5, 6, and 7, and those occur here. So we make sure that we've included all carbons and not added any extra carbons. Keep in mind that this is not an SN2 reaction. We are not taking a butyl anion and adding it here to kick out iodide. That is not how this mechanism works. You don't have to know this mechanism, which is handy for you, but it is important that you not draw it as an SN2 reaction, because we cannot do SN2 chemistry on an sp2 hybridized center. Something to keep in mind with this chemistry is that in the end you waste an entire R group because only one of the R groups on the cuprate transfers. So in synthetic design, you want the part attached to copper to be the cheaper part of the molecule. The other reaction I mentioned that organocuprates can do is SN2 chemistry. So this is a really great way to make a carbon-carbon bond between two sp3 carbons. So we have our Gilman reagent that we form from our organolithium and copper iodide. That gives us the organocuprate. We're going to transfer one of these alkyl groups in a backside attack on the primary alkyl bromide, kicking out the bromide to form the desired carbon-carbon bond. So a couple of quick reminders. When we're doing a cuprate SN2 reaction to form a carbon-carbon bond, the halide must be sp3, and the organocuprate can be alkyl as shown here, or vinylic, aryl, benzylic, etc. So now we have another synthesis problem, and I'll encourage you to try this one on your own, and we'll go over that solution during the discussion section. One quick hint I'll give you is that you always want to look at what bonds are already present in the available starting materials and in the target molecule. So if you compare the 6-membered ring containing starting materials with the product that I've shown, you can see that all of these atoms are contained in both of these, actually this one too. All of those are contained in both of the starting materials. And there is more than one way to make this compound, so if you can think of more ways, then feel free. Good luck. Lastly, here's a handy summary of all the things we've learned so far about these Grignard organolithium and Gilman reagents.